Hello everyone, my name is Gábor Dániel Balogh and I am going to talk about automatic parallelization from high-level abstraction for mesh-based application using the OPS and the OP2 libraries. First I'm going to talk about some difficulties developing currently high-performance parallel computational applications. Then I will introduce the differences between the structured and the unstructured meshes, and after that I will introduce the two libraries that this presentation is about, the OPS and the OP2. I will show a little example to how to use these libraries, then talk about a little bit about the optimizations performed automatically inside the libraries, and show some results that the library is capable of. So first of all, nowadays the hardwares that we are using, the GPUs and all of that, is rapidly changing and improving to overcome challenges, and also we have a considerable uncertainty on which platform we want to support, because we don't know which will be the winner or which will be the best choice for our application. And also for the newer hardware and coming the newer versions, we have increasing programming skills needed to get the best performance from these hardwares. So I'm going to show another approach to overcome this problem. If we split the high-level definition of the simulation we want to run from the parallel implementation of the problem, we can specify the whole simulation in the abstraction level. Then we can automatically translate this description to an optimized version and multiple optimized versions of the parallel implementations. So, these are the two types of grids that we are talking about, two different problems. For structured grids, we have implicit connectivity. Basically, we have a block, and we know that if we know the index of one element, we know all the index of all of its neighbors. So it's easily to parallelize based on this knowledge. But in unstructured grids, we have collections, we have nodes, faces, edges, and we have explicitly information about the connection between these elements. For example, we have a table that tells that for each edge it connects to cells and the indexes of these cells. And we get a much harder problem in terms of parallelization, because we have to calculate which chunk of edges, for example, can run parallel based on this connectivity information, and we have to keep track for every, let's say, every kernel that we want to compute. But so the question is right, why are we want to use unstructured meshes? But for many interesting cases, the structured meshes don't provide a proper solution for the problem. So let's talk about the two libraries that I'm introduced. Both OP2 and OPS is an open source project, and OP2 is based on the O+, the Oxford Parallel Library for Unstructured Solvers, which developed for CFD simulations on distributed memory clusters. And OPS, sorry. So OPS is based on the OP2, but with modifications and optimizations for structured meshes and applications. Both the libraries supports for C++ and Fortran codes. And for the higher abstraction level, it looks like a conventional library, but it uses a source-to-source translation model to give multiple implementations and optimize the source codes. Okay, so let's see what the abstraction we use for OP2. We have sets. We define the nodes, the edges, and everything that we need for the computation. Then we define the data sets that we use on these sets, and we define the mapping, the connectivity information between the sets. After, if we have this information, we can define the parallel loops that iterate through all of the elements of one set and access the data on the sets at most one level of indirection. That means if I iterate through the edges, then and I have the mapping that one edge is connected to these two cells, then I can use the data on these cells as well. But we have these two restrictions that all the iteration can be run in any order, and the mappings and the sets mustn't be changed in the whole simulation, during the whole simulation. The OPS has a very similar abstraction. Instead of sets, we use blocks, and the mapping, instead of mappings, we have stencils which describe how we access the data of the neighboring cells. And basically, it gets the same usage. In this figure, we see an unstructured mesh. We have cells with indexed with red and edges with black, and we have a one-dimensional data on both. And I'm going to show how it can be defined in the OP2 library. So we tell the number of edges and cells. We basically create the array which tells the connectivity information, and then we tell the library that there will be a set called edges, there will be a set called cells, and there is a mapping between edges and cells. Every edge has two neighboring in the cells, and then a name to this mapping. And then we can define the data on the sets in this very similar way. So we tell that we have the cells and one-dimensional data with doubles called cell data. Okay, and if we're done with this, we can create the operations on the sets. So, for example, we have a loop that iterates through the edges and adds the edge weight to the neighboring cells. We can describe it like this. So we give the implementation of one iteration. So we give, in the view of one edge, we give that it will do this computation. Then we give the description of the loop, which basically tells that here is the implementation, the name of the kernel. It iterates through the edges, and all the parameters for this operation. We access directly the edge data, and we only read it. And through the PE cell mapping, we access the cell data with offset 0 and offset 1, and we increment both of them. So how the library works? First of all, we will create the OP2 or OPS implementation of the application. Then we run the source-to-source translator in Python, and inside the source-to-source translator we have the optimizations, and we get the optimized source code and source files for our application. And after that, we can compile the application as always. So we link to our backends to provide the different implementation, different parallelization techniques. And after it, we get the binary, so we can run our application. And these are some examples which optimizations are done with the source-to-source translator. For example, for better memory accesses on GPUs, we have this transformation on data layout. And for example, if we want to use MPI and multiple nodes, we can automatically split or mesh to parts, and because we know the operations which data we will read or write, we can determine when and how we should send our messages through the MPI. So it can be used to minimize the MPI messages sent automatically. And also the abstraction makes it possible to have an automatic checkpointing. That basically means we save the data in every X minutes, and if some crash happens, we just read back the data and don't have to start the whole simulation from the beginning, just continue from the last good results. And also, based on the memory data accesses, we can queue up the kernels, and if we do some optimizations and find out that we can reorder the kernels, then we can run it parallel also. So for showing some results that we get with the libraries, here's a mini application, the Cleverleaf, which is a structured 2 or 3D hydrodynamics simulation, which explicitly solves the compressible Euler equations. And if we compare the OPS library results with the original handwritten and optimized code, we could see that on CPU we have almost the same performance as with the handwritten code, and on GPUs as well. So we can tell that our abstraction and translation could generate nearly optimal performance codes. And in case of MPI and multiple nodes, we can show that on the Titan supercomputer we have almost the same scaling as if we use the handwritten and optimized code as well. And for the OP2 library, I give this example, the Hydra code, which is an unstructured mesh-based CFD application for simulating turbomachinery of aircraft engines. It's basically written with the O+ library, the predecessor of the OP2, and in Fortran. And after porting it to OP2, we, in single node with GPUs, we have, of course, better performance than the original old version. And also the scaling is almost the same as the original version. So there is some other applications that already mapped to OP2 and OPS. There is the airfoil, which is nonlinear 2D discrete airfoil simulation. There is the VONA, which is the numerical model for the whole life cycle of a tsunami waves on unstructured grids. And for the OPS, there is the T-leaf, which solves the sparse system of linear equations without actually constructing the sparse matrix, or the OpenSVLI, which is a compressible Navier-Stokes solver. So altogether, we can say that the OP2 and OPS abstraction can facilitate the development of high performance applications, because we have to give the abstract description, and we get all the implementations for CUDA, for OpenCL, OpenACC, and all the other. And we get nearly optimal performance. Moreover, we don't have to bother us with optimizing our code, because a bunch of optimization done by the source translator. So this is also facilitates our development process. And we can get a future-proof and maintainable source code base, because we only have the abstract description that we give, which is doesn't imply any of the parallelization models or anything else. Just tells that the simulation looks like this, and all the other implementation concern stuff is inside the translator. And thank you for your attention.
Okay, let's see everyone. Time for questions.
I wanted to ask about the source-to-source translation part. If I understood that it's a set of Python scripts that translate from the front end to the backend code. And how robust is that in terms of C++? And the code you showed, it's a naked C-style array.
Yes.
And for example, the array of structure versus structure of arrays transform. Can the source translator detect, for example, a vector of tuples and make the same change? Or
data is always stored in arrays in the library, but we can define data with more than one dimension and do the translation on that type, if I understand right the question.
So you say that the API only accepts naked pointers as the entry point to define the data?
I think it's yes, but István could answer it better. I think yes.
Further questions?
Thank you. Can you mention the specific optimizations that you know of the source translator performs?
Yeah, so that's the data layout transformation, and for the OPS library there is tiling and check the caches also.
Thank you.
No more questions. So let's think up again.